All right, so continuing with Chapter 8, our geomorphic units and channel form, our next topic is looking at hydraulic geometry, which is a way to look at the relationships between the driving variables of flow and sediment, so water flow and sediment flow, and the resulting channel geometry. So each cross-section has been shaped and dimensioned over time to accept that range of flows, and there's been a lot of work looking at those relationships. It doesn't prove causation, and it's just sort of looking at some conventional relationships in our way to try to understand rivers. The first thing that humans want to do is we want to classify things, right? And so this is a way of trying to classify rivers and look at patterns that we can see between rivers of different flow rates with different amounts of sediment, and does that affect what their channel looks like. Oh, right. So back to this notion of equilibrium. We can define equilibrium numerous different ways: non-silting, non-scouring, whether it's adjusting its slope, whether it has consistent mean measurable behavior over a given period of time, or whether it's just stable in some sort of dynamic or quasi-equilibrium. And one of the tricky things with this notion of hydraulic geometry is it is presuming an underlying assumption of equilibrium, that the channel has experienced the same discharge and sediment flow for a long period of time and therefore has adjusted to that. So it started with what was called regime theory, which was pioneered by hydraulic engineers in the late 1800s in Africa. They were designing irrigation canals, and they were very concerned with stable channel design. They wanted a stable channel that's non-silting, non-scouring, so they wanted to be able to adjust the channel, the width, the depth, the slope, the shape of the channel, so that it would not silt up and not scour, given the flow that was provided to it over a long period of time. So when we talk about a regime channel, is a stable channel, is an equilibrium channel, is a graded channel. So those terms are all synonymous. And again, back to our same diagram we've looked at before, we have our inputs of water and slope, stream power, flow energy, and sediment that come into our system. If it's in equilibrium, it's in regime, it's stable, it's not moving around a lot, it's not static, but it's not undergoing changes. If it's not in equilibrium, then it's going to have to adjust. It's going to either aggrade or degrade or widen or narrow or migrate. All right, so if our channel cross-section adjusts over time to accommodate this range of flows, how would you expect the relationship between the discharge and the width and depth to look at a station? Well, we've already looked at this with just a rating curve, right? We know if discharge goes up, depth goes up. And what would you expect if discharge goes up? The width is also going to increase. What about if we go downstream on a river? As we move downstream, discharge goes up, the river gets bigger, it gets wider, and it gets deeper. So basically that's the gist of a hydraulic geometry relationship. What is the relationship between the channel dimensions and the discharge? So hydraulic geometry at a station. So we're at a single cross-section and the discharge is going up and down. So single cross-section, varying discharge. So we're at cross-section B. The number is time. So 1 is a low flow, 2 is a moderate flow, 3 is a high flow. So how does the geometry of the channel vary from flow 1 to flow 2 to flow 3? If we're looking at downstream hydraulic geometry, now we're going to look at cross-sections A, B, and C as we move from the headwaters downstream in the channel. And but what we have to do is choose a single discharge. But it's not a single actual like CFS magnitude of discharge, because obviously the channel at A is only going to carry a much smaller amount of water than the channel at C. And so what we have to do is pick a consistent measure of discharge that we can compare at different places in the channel. And so usually what we do is bank full. So we'll say, what's the channel geometry at A at bank full? What's the channel geometry at B at bank full? What's the channel geometry at C at bank full? So you could use bank full, 2-year frequency flood, something like that. And the way this all fits together, so here's our river system. We have going downstream cross-sections A, B, and C. At cross-section B, we're looking at the geometry as it changes with time. And so we could look at the discharge increasing and the velocity the velocity increases. The discharge increases from time 1 to time 2 to time 3, and the depth increases from time 1 to time 2 to time 3. And then same thing with width. And so this is what a at a station hydraulic geometry relationship is looking at, is what is the discharge at a single cross-section, and how does it relate to width as discharge changes. We can also look in the downstream direction, so from A to B to C, and in this case they're doing the log of the mean annual discharge. So discharge goes up on the x-axis. How does width change? And yes, of course width is going to change as we go from upstream to downstream. How does depth change? And velocity actually doesn't change that much. So we'll come back to these, but I just wanted to kind of set up the scenario of how this actually works. So hydraulic geometry equations in this simplest form assume that discharge is the dominant independent variable that determines the shape of the channel. So we're not thinking about sediment flow right now, right? So if we were to, let me back up a slide, we have this width versus depth plot here, right? So if we were to plot a regression line along that, and it's the log of the width and the log of the discharge, we get a power function. The width is equal to some constant a times the discharge to the exponent b. Same thing for the depth hydraulic geometry equation, for velocity, and for slope. And we know that discharge equals width times depth times velocity. So we know then if we plug in a times q to the b for width, and we plug in c times q to the f for depth, and we plug in k times q to the m for velocity, then we know that b plus f plus m has to equal 1 in order for q to equal that. So we know that the exponents of the width hydraulic geometry equation plus the exponent of the depth hydraulic geometry equation plus the exponent of the velocity hydraulic geometry equation have to sum to 1 so that q can equal q. A little nuance of hydraulic geometry. Okay, so let's look at some examples. So these are from the Powder River in Montana. We have discharge, and notice that it is a log scale on the x-axis, discharge in cubic feet per second, and we have width and depth and velocity. And discharge increase, an increase in discharge leads to an increase, well, I gotta take that back. An increase in discharge is correlated to an increase in width. So the higher the discharge, the higher the width. As discharge increases, the depth has a little steeper correlation. The number here is the value of this exponent, right? So the exponent for width has a value of about 0.3. The exponent for depth has a value of about 0.4. And for velocity, 0.3. And we also see there's similar correlations with slope and with suspended sediment discharge, where as discharge increases, there's a very high correlation, and suspended sediment discharge can increase a lot. And we see that in a lot of rivers. All right, some more. In larger rivers, as we're still at a station, as we increase, sorry, I'm checking the, as we increase the discharge, we see less change in width and depth. And so this Watts Branch has a drainage area of only 3.7 square miles. Seneca Creek is 100 square miles. And the Amazon, of course, is really big. It's at the Obidos station, 1.9 million square miles. And so you can see the depth and the width are a little flatter for the Amazon, but velocity is actually pretty steep. All right. So those are at a station hydraulic geometry equations. Now downstream, so we're moving in the downstream direction, so discharge is increasing as we go down. We know discharge goes up as tributaries enter. We choose the same Q that we're going to use in all of our stations. Oh my goodness. Sorry. And in this case, it's mean annual discharge, so mean annual flow. And this is using rivers in the Powder River Basin in Wyoming and Montana and tributaries to the Powder River. And here's our width relationship, our depth relationship, and our velocity relationship. And what we find with downstream hydraulic geometry is there tends to be a pretty consistent relationship between how discharge increases with width as you go downstream, and the exponent value tends to be about 0.5. So that means that the discharge correlates as proportional to the square root of the depth. And that's a pretty consistent relationship in a lot of rivers. And then we can see here's our depth relationship, and the velocity one's a little flatter, not as big of a change in velocity as we go downstream, and not quite as consistent. Oh, let me back up. They also plotted on here, oh right, these are all the Wyoming rivers. These, oops, too fast. We have a bunch of different rivers, so I didn't point that out, that we're looking at rivers of different size. Number 7 is the Mississippi up here, so obviously you're way over here, much higher discharge. And you even have irrigation canals, and the ones that kind of deviate, number 6, the Loup River in Nebraska, which I actually don't know much about. But other than that, the relationships are actually pretty consistent. So, and this is true in a lot of cases. So some of the downstream hydraulic geometry equations that we see are, well, the earliest one, so this is Kennedy doing regime theory, the non-silting, non-scouring channel. The velocity is proportional to the depth to the 0.64. Leopold and Maddock in the 50s published this big definitive paper that's cited still extensively. And they found that the width correlates to the discharge to about the 0.5, the depth to about the 0.4, velocity typically we see now about 0.1, and slope to about minus 0.3. So others have extended this approach to include other factors: vegetation, bed material, bedload transport, and degree of lateral deviation, which has to do with meander bends. So A and C are at the same place. A is at low flow, C is at high flow. B and D are the same place. B is low flow, D is high flow. So here's our channel at low flow from A to B. Same channel, high flow, C to D. So, all right, so this is a similar diagram to one we looked at earlier, looking at the attestation versus downstream hydraulic geometry equations. So the downstream equations are represented by the solid lines, and the attestation hydraulic geometry equations are represented by the dashed lines. So what we can see is the difference in the relationship between discharge and width attestation versus downstream. So how does width change with discharge at the same cross section, and how does width change with discharge as we move downstream? So you can see from A to B and C to D, that's downstream. At low flow and high flow we have similar slopes. Okay, so we can see from A to B, which is going downstream at low flow, C to D going downstream at high flow, we have the same slope. From A to C, which is the same cross section, low flow to high flow, we have one relationship, and then B to D, low flow to high flow, a similar slope. These two lines, A to B, C to D, that's the Q equals W to the 0.5 equation. Okay, check out depth. Doesn't matter. Downstream or attestation, similar relationship. And remember, discharge versus depth is kind of similar to a rating curve. A rating curve is water surface elevation, but depth is still, it's how the water surface is going up and down. Velocity doesn't change much downstream. Velocity changes more attestation as discharge increases. Suspended sediment changes a lot attestation when discharge goes up. Suspended sediment does not change as much, it still does go up as you go downstream. Channel roughness, it goes down as discharge goes up. And that relationship is pretty similar whether we're at the same cross-section or we're going downstream. And slope decreases as we go downstream, and slope might increase a little bit as discharge goes up. That's not a strong relationship. Whew. Okay. Another example of a hydraulic geometry relationship that actually has a very strong relationship, and it will lead us through how we can use drainage area as a surrogate for discharge. So we know that in most watersheds, there's a very strong relationship between bankful discharge and drainage area. So if you're in the same region and the same climate and the same watershed, you can often see this strong relationship. So here we're on the Maryland Piedmont. As drainage area increases, bankful discharge increases, R-square of 0.93. So what we can do then is use drainage area as a surrogate for discharge. So this is another way to get at a hydraulic geometry equation where we take drainage area and regress it against our bankful characteristics, such in this case cross-section area, width, and depth. So estimating width as a function of the drainage area, estimating depth as a function of the drainage area. So just another way of getting at these hydraulic geometry equations. So the average sort of typical values for the exponents, that Q is equal to the width if we're doing downstream hydraulic geometry, width to the 0.5, if we're at a station, width to the 0.26, depth again about the same, velocity flatter when we're going downstream, steeper relationship at a station. So velocity changes more at a station as discharge increases than it does as discharge increases in the downstream direction. Okay, slope, because slope decreases as we go down. All right, so it's a little tricky to include other parameters, but people have tried. So some other things, all of these things are going to influence the flow characteristics: sediment load, sediment size, cohesion of bank material, riparian vegetation, geomorphic history. It's hard to quantify these. How do you come up with something you can regress a quantity that's about riparian vegetation? So not much data on bed material discharge, that would be the best. And how do we quantify the influence of bank vegetation on bank stability and erosion? So it's kind of tricky to include those. But my former PhD advisor actually tried to do this, and he created some hydraulic geometry equations that included 4 independent variables: discharge, sediment size, a Shields parameter, and then a parameter that included the effect of radius of curvature on the flow, and came up with 4 independent equations that look like this. So you guys have to memorize those. Just kidding. And then with another grad student, he developed what he calls a semi-theoretical set of hydraulic geometry equations that are based on the 4 fundamental hydraulic relationships of continuity, the energy balance equation, or flow resistance, sediment transport, and then some of the mechanics of secondary flow. They used 835 rivers, and this is applicable to alluvial channels with wide-ranging grain size beds, and this is what they came up with. So relating depth to discharge, whoa, what happened? Oops. Relating depth to discharge, grain size, and slope. Relating width to discharge, grain size, and slope. Relating velocity to discharge, grain size, and slope. And relating critical shear stress to discharge, grain size, and slope. And you calculate the m value, which you can see the exponents all have this m value based on a relationship between depth and grain size, and you have to iterate to make it work. Alrighty, so that's it for hydraulic geometry equations. There will be a little assignment, and I'll have a little video explaining how the assignment works up on D2L. So let me know if you have any questions.